All right, guys, here's the challenge of the day. So I've pretty much been recording all evening. My last recording, I got 18%. So the question is, can I do this more or less flawlessly so I don't have to retake it and I can get it all done tonight? We'll see. So hey there, drinking buddies. Welcome back to Scientific Drinking. Tonight's episode is going to be on high velocity plume ejecta and electrical fields and all kinds of weird stuff that happens to dust. And yeah, so this is again based on some of the recent work I've published, and I'm going to share with you. Again, if you can't explain it simply enough for people to understand, then you don't understand it well enough. So I'm going to prove to myself and the world that, damn it, I understand what I publish. So in this episode, we're going to talk a little bit more about space dust and specifically how this super high-speed dust can end up with putting a dent in your plans to explore the moon. Cheers. So tonight I'm drinking Hakuna Matata Tropical IPA. I'm pretty sure I've drinking this before in another episode. It's delicious, man. So first of all, let's talk about the amazing people that helped me get this work done. A couple of them are over at NASA, Jay Phillips and Jim Montavani. One of them is my mentor, Jim. And of course, there's Phil Metzger, who's kind of a legend in the small and specific field of lunar dust. And then, of course, a couple of my other colleagues, contractors of NASA, Bruce Link and Dan Bacheldor. And Dan especially has been a great help to me understanding some of the dynamic charge environment around the moon, which is just not intuitive at all. So let's talk about background first. To understand the problem that we're dealing with, take a look at this footage. This shows both real and simulated situations of landing on the moon. Some of it's from Apollo, some of it's from promotional videos, but in all of them you see a lot of dust are getting kicked out. And in the case of Apollo, those landers were small, only 5 metric tons or so. But the problem is even more pronounced coming up on the Artemis program, where the landers can exceed 40 tons, or if they go with Starship, it's going to be even bigger. Granted, Starship's going to land with some nose cone thrusters to mitigate dust. Let's first consider landing here on the Earth. I'm sure many of you have seen the videos of the Falcon 9 first stages landing after launching a rocket, especially the boosters on the Falcon 9 Heavy. Those kick up a lot of dust, and that's just on a landing pad. That's not even in dirt. Here's another video of a Maston aerospace lander landing in dirt here on Earth. Now that's a tiny little lander, and see how much dust it's kicking up. That is extraordinary. And finally, another one from Blue Origin, who have a very minimalist landing pad out in the Mojave Desert, and it kicks up a lot of dust. So even here on Earth, it's going to be a problem, but on the moon, where there's no air to slow it down, it's actually a pretty big problem. Recent estimates based on the amount of dust that was kicked up for the Apollo lander scaled up to something like the 40-ton Artemis-sized lander predict that up to 90 tons of regolith and dirt and dust are excavated just from the lander alone. That's a tremendous amount. A lot of that speeds off at several kilometers per second. And so we want to understand where that dust is going and how much of it is really dangerous. So to understand where this goes, we have to understand more about the dust itself. For an in-depth look at lunar dust, I recommend you turn to my other video that talks a lot about its physical properties, and that's in the link below. But in a nutshell, this stuff is really small and electrically charged. If you blast it at high velocity, it's going to interact with the charged environment both on the lunar surface and in the orbital environment as well. At the South Pole, that by itself could be a problem. I mean, you see, the moon doesn't really have an atmosphere to protect it from the sun's rays, so it's bombarded by X-ray and UV light all the time. On the sun-facing side, it's positively charged from all that light, and on the other shadowed side, it's influenced by the lunar wake, which has its own negative charge. Now that's according to Artemis. No, not this Artemis, that Artemis. Near the South Pole, where we're expecting to land for the Artemis program, you're always near the terminator. And there's long, elongated shadows from craters and mountains and valleys, and that just makes a really complex charge environment because you don't know where it's positively charged and where it's negatively charged. It's not always indicated by the shadows. That plus levitating, yeah, that's right, levitating dust caused by the charged environment makes it very difficult to understand all the dynamics that go on the surface. But we can approximate it, and that's what I did in the paper, just kind of assumed that the moon is mostly spherical and you're kind of taken off from a flat plane that's in the sunlight. Besides, for the purposes of this simulation, the dust is moving very fast, so it spends less than a second in this near lunar surface environment where the charge is all kinds of wonky. So we can assume a simple electric charge of 1.1 microcoulomb per square meter. But our issues with electric field doesn't end there. As soon as you leave the surface of the moon and get into the lunar orbital environment, you're bombarded with more electrical charges. You have the magnetotail of the Earth, which you pass through every orbit. And then again, the amount of magnetotail you are exposed to changes because the moon is inclined by 5 degrees. And where you are in that inclined orbit is not a trivial thing to decide or figure out. Then, of course, there's the solar wind, the solar electric field. It all gets so complicated. And these dust particles are so incredibly small. We're talking about micrometer-sized pieces of dust. The smaller that dust particle is, the more subjective it is to the solar wind and the electrical fields. And the more likely it is, it's just going to be carried away. And that's exactly what happened to Mars's water when it got into the upper atmosphere later in its formation. It just got carried away by the solar wind because Mars was too light to hold on to the water. Same thing with hydrogen and Earth. Why don't we have any hydrogen in our atmosphere? Well, the Earth is too small and the solar wind is too powerful, so it just blew all that hydrogen away into interstellar space. The same thing happens with some of this really fine dust that's kicked up during these landings. It just gets carried away by the solar wind. So alright, so now we've listed all these things that we need to consider just to start our simulation. Now let's actually run our first iteration. This shows 5,000 particles all being integrated at the same time. The purple ones are in the shadow of the moon while the green ones are in the sun. By running a simulation like this over and over again with slightly different properties, we can begin to build a big picture about how this dust responds to its environment. Most of this needs a lot more work. I mean, we're running on just some Apollo data, some observations from orbit, and a few tricks here and there. You know, that's pretty common in science. There are more things to explore than I have time for.
Yes, science!
But in a nutshell, most of the dust particles that are smaller than 10 microns wander off into interstellar space, while ones that are bigger than 10 microns don't really get fast enough to escape or re-impact the surface very quickly. It's the 10 micron range that really seems to be interesting. They hang around in space for long periods of time and re-impact near the landing site. This is kind of what we were expecting from rudimentary models. We thought that the landing site would be bombarded by this higher velocity dust, but by how much we didn't really know. Now we have some kind of estimates saying that maybe if you're close enough to the landing site, let's say 1 kilometer away, and your base takes up a 1 square kilometer footprint, you can expect from an Artemis-sized lander 18 impacts or so. A smaller lander that's such as 10 metric tons might only produce about 8 impacts. And they're very small pieces of dust, so the damage they do really depends on what material you have your spacecraft or spacesuit or base made out of. This is kind of what I was expecting, right? You expect it to re-impact the surface after a certain period of time. But what I was also expecting was for something like the Gateway to be in danger from all this dust that's being kicked up. And that's where I was wrong. Turns out that all this dust that gets kicked up really just re-impacts the surface faster than it takes the Gateway to complete one single orbit, which takes about 6.5 days. I couldn't find a single piece of dust that crossed Gateway's 100-kilometer keep-out sphere of influence. So the key takeaway to this experiment is that if you're going to build a base on the moon, the absolute best plan is to build a landing pad so that you aren't going to kick up this much dust in the first place. Now, building a landing pad isn't simple. Again, that's another thing that's worthy of an episode in and of itself. But when you think about it, a moon base already has to deal with a lot of problems. Radiation, micrometeorite impacts, just the dust itself that's kicked up from everyday activities that gets into your spacecraft and slows down your equipment. Why add more problems to that when it's not a big deal to build a landing pad? Well, not too big of a deal. Probably. We'll see. The research has, if anything, introduced me to a huge number of variables that exist for this problem and how simplifying the problem really isn't a simple process in itself. Really, there's only so many things we can do. In the future, we're eventually going to have to send someone over there to take some measurements, to record some videos, to dig up some lunar regolith and actually see where this stuff goes. Any volunteers? Cheers.